This is tetraethyl lead. Its addition to fuel in 1923 has cost $13.5 trillion globally. It's caused the estimated deaths of 5.5 million people, and it's stolen 765 million IQ points from children under 5. It's been 23 years since leaded petrol has been banned in Australia, and we've seen a reduction in crime rates and premature deaths. However, tetraethyl lead still remains. It is used as an anti-knock additive in aviation gasoline, AVGAS, used by light aircraft, like Cessnas. And you would think that nearly a century after its introduction, having experienced its destructive consequences, tetraethyl lead and leaded fuels would have been banned. To understand why they still remain in aviation, we need to go back to its inception. In the 1920s, car manufacturers were encountering a problem called knocking. Knocking occurs when the fuel-air mixture inside the engine explodes rapidly rather than burning smoothly. This results in the engine running rough, loud, and can cause severe damage.
And inside of it. But listen, you old-timers, hear that? And here's a picture of the villain on the soundtrack. Now you can sing. Did you ever see a knock-knocking? Well, I did.
This brings us to 1921, when a General Motors engineer called Thomas Midgley Jr. suggests a new, highly effective anti-knocking additive, ethanol. However, General Motors knew that ethanol could not be patented and it was considered too expensive. So Thomas Midgley Jr. discovered tetraethyl lead. It was extremely effective as an anti-knocking agent and required far lower concentrations in fuel than ethanol did. It was extremely cheap and, more importantly, patentable. However, it had one problem. It was extremely toxic. When leaded fuels were first being rolled out, Thomas Midgley Jr. was in bed suffering from severe lead poisoning. So leaded fuels were introduced and they quickly became routine. After World War I, engine designs advanced rapidly, with the addition of the supercharger and later the turbocharger increasing performance. But as engine power increased, so did its susceptibility to knocking, with fuel quickly becoming the main constraint. Advances in refining in the 1930s and the addition of tetraethyl lead to fuel allowed its octane rating to increase, which means an engine could produce far more horsepower from the same volume without any knocking. The octane rating is the number you see at the petrol station, such as 91, 95 or 98 unleaded, and is formally known as the research octane number, or RON. The RON indicates the fuel's resistance to knocking and is determined by running a test engine under controlled conditions with two different reference fuels, then standardizing the amount of knock produced. Iso-octane was chosen as the benchmark with a value of 100 since at the time no one thought its anti-knocking properties would be surpassed. In contrast, N-heptane was selected with a value of 0 because it knocked readily in any engine. For example, 91 unleaded fuel has an octane rating of 91, meaning that it behaves like a mixture of 91% iso-octane and 9% N-heptane in terms of knocking resistance. However, the industry realised that the research octane number had limitations, as it was not representing the actual knocking resistance in the real world. So, the motor octane number MON was created, running the same test engine at higher temperatures, pressures and RPM, and using the same standardized fuels of iso-octane and N-heptane. The system used to measure the knocking performance of avgas is slightly different than that of motor gasoline. Instead of having a single octane rating, avgas is first run in a test engine with a very lean mixture to simulate cruising at higher altitudes where there is excess air. It is then run with a very rich mixture to simulate high power situations, such as takeoff where there is excess fuel. For this reason, avgas is often shown as having 100-130 low lead. where the 100 represents the lean mixture corresponding to the motor octane number rating, whereas the 130 represents the octane number of the rich test, which is developed by ASTM, the American Society for Testing Materials, which uses a separate turbocharged test engine. In essence, avgas needs to be able to perform over a wide range of temperatures and pressures without knocking. There have been 3 grades of avgas used within the general aviation industry. These are defined by the ASTM 91-21 standards, which outline the properties, composition and additives permitted. First, we have 100, which is the original fuel used in general aviation, containing a maximum of 1.12 grams of tetraethyl lead per litre. Then, to reduce lead emissions, 100 low lead 100LL was introduced to Australia in the 1980s, containing a maximum of 0.56 grams of tetraethyl lead per litre. Then finally, 100 very low lead was created as a standard, with a maximum of only 0.45 grams of tetraethyl lead per litre. There is limited information surrounding the introduction date and current availability of 100 very low lead fuel. However, material safety data sheets from current 100 low lead suppliers in Australia indicate that the 100 low lead threshold is below that required by 100 very low lead. But how bad are lead emissions from avgas, considering the relatively small number of aircraft operating, less than 10,000, and the wide distribution area compared to historic car usage? Is lead really any more dangerous than whatever else is in avgas? What are the effects of exposure? And what happens if you get it on your skin? Tetraethyl lead is a molecule with 1 atom of lead surrounded by 4 ethyl groups. The prefix tetra is of Greek origin and means 4. An ethyl group is simply 2 carbon atoms surrounded by hydrogen atoms, all connected by a single bond. A common misconception is that exposure to leaded fuels such as avgas is equivalent to exposure to elemental lead, such as what's found in these fishing weights. However, because tetraethyl lead is an organic molecule, it is easily absorbed through the skin and makes its way into the body, whereas elemental lead is primarily toxic through oral exposure. For example, if this were instead full of tetraethyl lead and there was no container, I would likely receive a fatal lead dosage. When tetraethyl lead undergoes combustion, it is turned into lead oxide, which can accumulate in the cylinder and exhaust valves, lowering efficiency and creating spark plug fouling. Fouling occurs when lead oxide deposits build up on the spark plug, preventing the spark from properly forming. To prevent this, a lead scavenger is added, such as dibromoethane, which instead forms volatile lead bromide compounds which can escape the cylinder and make their way into the environment. The ASTM standard for leaded fuels states that for every atom of lead in the cylinder, there must also be 2 atoms of bromine to make sure that lead oxide does not build up. Several studies have shown a correlation between blood lead levels and populations living downwind of airports in the United States and United Kingdom. For example, children were 25% more likely to have a lead level of 5 micrograms per deciliter when living within 1 kilometre of an airport, 16.5% more likely between 1 and 2 kilometres, 9.1% more likely between 2 and 3 kilometres, and 5.4% more likely between 3 and 4 kilometres. Beyond 4 kilometres, the data was inconclusive. This exposure is likely due to 2 factors: historical lead contained within the soil and environment, and active emissions from aircraft taking off and landing. There is no safe level of lead exposure, and children are particularly vulnerable. Even a blood lead level of 5 micrograms per deciliter, which is observed within populations near airports, falls within the range where significant cognitive effects have been documented. Studies show a drop of 7.4 IQ points as blood lead levels increase from 0 to 10 micrograms per deciliter, with further losses of 2.5 points between 10 and 30 micrograms per deciliter. Interestingly, the greatest cognitive impacts seem to occur with initial exposure, as cellular protective mechanisms appear to activate after subsequent exposures. This means that even seemingly low accumulations of lead, such as 5 micrograms per deciliter, have a potential to meaningfully impact a child's cognitive development and overall well-being. What is most concerning is that Australia does not monitor or test lead emissions from piston-powered aircraft, even though 70 million litres of avgas was sold in 2024, containing 24.5 tonnes of tetraethyl lead. That figure reflects sales for just 1 year, and while it represents fuel purchased rather than burned, it highlights the scales of potential emissions. Without domestic data, we have little understanding of the true extent of the environmental and atmospheric lead pollution. Because lead bioaccumulates, there is a very real risk of harmful concentrations building up around high-traffic airports. Equally troubling, there is no monitoring of lead exposure among general aviation workers. Data that would be critical for understanding how repeated contact with avgas fumes and liquid affects blood lead levels. Given the well-documented dangers of lead, Australia's lack of emissions and exposure monitoring seems not only complacent, but dangerously negligent. But hope is not lost. The fuel and engine technology needed to transition to unleaded alternatives already exist. The challenge is not technical innovation, but economics and the resistance from both industry and government to adopt new technology. In 2023, the US Environmental Protection Agency issued a public health endangerment finding regarding lead pollution from avgas, and California has passed legislation to ban it by 2031. Despite this, engine manufacturers such as LYCOMING have resisted the shift, suggesting that leaded avgas could remain in use for another 15 years, and showing little willingness to test unleaded fuel replacements. Currently, 2 main companies are developing and producing unleaded avgas: General Aviation Modifications Incorporated, GAMI, and Swift Fuels Incorporated. Both offer 100-octane unleaded fuels, but they take different regulatory approaches and use different fuel chemistries. While G100UL, GAMI, and 100R Swift Fuels are both interchangeable with 100 low lead, they are not interchangeable with each other. GAMI choose to pursue a supplemental type certificate STC for G100UL rather than seeking an ASTM certification like existing leaded fuels. An STC is an FAA-approved certificate authorizing significant aircraft modifications, such as using a new fuel. While an STC allows broad application across piston engine aircraft, it does impose additional costs and administrative requirements on owners. GAMI likely selected this approach due to the time and expense involved in ASTM certification. G100UL achieves its high-octane rating without lead by incorporating a high percentage of aromatic amines and aromatic hydrocarbons. Swift Fuels, in contrast, has obtained ASTM certification for its 100R fuel, with plans to achieve fleet-wide approval within 3 years. 100R attains a high-octane rating using ETBE, ethyl tributyl ether, derived from ethanol, and is fully compatible with 100 low lead. Both companies have expressed concerns regarding each other's fuels. Swift Fuels claims G100UL may damage paint and rubber components, while GAMI warns that ETBE could pose a pilot incapacitation hazard in the event of an in-flight fuel leak and is potentially carcinogenic. EPE is classified as a likely carcinogen by the EPA, though ordinary automotive gasoline is classified as a Group 1 carcinogen by the World Health Organization. It is difficult to assess the validity of either company's claims without independent studies. However, since both G100UL and 100R are FAA approved, it is reasonable to assume they meet safety standards. Because the 2 fuels are incompatible with each other, it is unlikely that both will be stocked at the same airports, creating additional barriers to widespread adoption of unleaded avgas. Furthermore, the price of each fuel is expected to be higher than existing leaded avgas, providing an additional economic disincentive for operators to switch to unleaded options. But what does the future hold for avgas in Australia? Without government intervention to phase out leaded fuel, it is unlikely that unleaded replacements will see widespread adoption, particularly since they may come at an increased cost. Government action is critical. Even when unleaded alternatives exist, regulatory approval remains a major barrier. In Australia, the Civil Aviation Safety Authority CASA addresses this in Airworthiness Bulletin 28019. CASA allows unleaded fuels to be used only when it is listed as an approved fuel in an aircraft or engine manufacturer's documentation, or when approved by a recognised National Airworthiness Authority, such as through an FAA Supplemental Type Certificate (STC). This means that Australian aircraft can currently use unleaded fuels from suppliers like GAMI or Swift Fuels, provided that the aircraft holds the appropriate FAA-issued STC. Some aircraft engines can even use automotive unleaded gasoline under an STC, though suppliers may be hesitant due to the challenges in ensuring stringent quality control required for aviation usage. One potential long-term solution is transitioning legacy aircraft to engines capable of using Jet A1. Diamond Aircraft have already demonstrated that Jet A1 powered aircraft operate reliably in models such as the DA62. Jet A1 is the same fuel used by airliners and contains no lead, making it an inherently unleaded alternative. However, given that the average age of general aviation aircraft in Australia is 37 years, this approach is unlikely to be viable for the majority of the fleet. Without decisive action from industry or government, environmental lead contamination is likely to continue. The technology to eliminate leaded avgas already exists, yet Australia has made no commitment to phasing it out. This inaction, coupled with the absence of comprehensive data on aircraft lead emissions and blood lead levels, is both complacent and borderline negligent.